Imagine staring into the night sky. You're looking at light that's traveled for millions of years just to reach your eyes. A silent canvas of stars. Calm, eternal, unchanging. But space isn't calm, and it isn't understood. For everything we've discovered, for every black hole, every galaxy, every theory scribbled onto a whiteboard, there are still questions we cannot answer. Some of them are small, others are so big they challenge the very structure of the universe. A star that dims with no explanation. A powerful radio signal heard only once, never again. A hole in the sky colder than anything around it. These aren't the inventions of science fiction. They're real, recorded, studied, and still unexplained. In this video, we'll explore the most baffling cosmic mysteries known to science. Some may be solved in time. Others may lead to discoveries we haven't yet imagined. But for now, they remain open questions. This is the edge of human knowledge, and it's far darker than we'd like to admit. These are the unsolved mysteries of space. In 2004, scientists using the Wilkinson Microwave Anisotropy Probe, WMAP, noticed something odd. They were studying the oldest light in the universe, the cosmic microwave background, or CMB. A faint glow left over from the Big Bang spread across the entire sky like thermal fingerprints from creation itself. This glow isn't perfectly uniform. It has tiny fluctuations, ripples in temperature, less than 1,000th of a degree. These ripples are expected. They're what gave rise to galaxies, stars, and planets. But in one particular region of the sky, something was off. It wasn't just slightly cooler, it was significantly colder, far more than the surrounding space. A vast patch, over 1 billion light-years across, sitting like a bruise in the cosmic fabric. Scientists called it the cold spot, and at first, no one was sure what to make of it. Maybe it was a glitch in the telescope, maybe it was random noise, a statistical outlier in the background data. But then, a second mission, the Planck satellite, confirmed it. This wasn't an error. There really was a hole in the sky, a place colder than the early universe around it, and no one knew why. If the cold spot couldn't be explained by dust or voids, then maybe the answer lies beyond the universe itself. In 2007, two cosmologists, Laura Mersini-Houghton and Richard Holman, proposed a different idea. What if the cold spot is a scar, a bruise, left behind when our universe collided with another? According to string theory and certain models of cosmic inflation, our universe may not be alone. It could be just one bubble in a vast multiverse, where countless other universes expand, interact, and sometimes overlap. And if two of those bubbles collided early in their formation, it could leave a visible imprint in the cosmic microwave background. A disruption, a distortion, a temperature anomaly that we'd still see today. That's what Mersini-Houghton believes the cold spot might be, evidence that our universe isn't self-contained. But this idea isn't just sci-fi, it's based on inflationary theory, the rapid expansion of space in the first tiny fraction of a second after the Big Bang. And while most physicists still view the cold spot as a statistical anomaly, this multiverse explanation has been taken seriously enough to be published, peer-reviewed, and discussed at length in cosmology circles. But here's the challenge. If we did collide with another universe, we may never know what that universe was, or whether it still exists, or whether others are still out there, just beyond the cosmic horizon. For now, all we have is a cold patch in the sky, and a theory. Despite all the theories, from supervoids to multiverse collisions, there's one explanation that scientists have never fully ruled out, that the cold spot might be nothing, a random fluctuation, just noise in the cosmic background. Statistically, the cosmic microwave background is expected to have outliers, patches that are slightly hotter or colder than the average. The cold spot is unusual, but not impossible. Some studies estimate there's a 1 to 2% chance that a spot like this could occur naturally. No exotic physics required. That's not likely, but in science, unlikely doesn't mean impossible. If you flip a coin 100 times, you might get 10 heads in a row. You'll be surprised, but it doesn't mean something's broken. It just means probability played its hand. The same might be true for the cold spot. The universe is big, And when you're mapping billions of light years, even the smallest errors or fluctuations can be mistaken for patterns. There's a term for it in statistics: apophenia, the tendency to see meaning in randomness. We might want the cold spot to be something more: a message, a rupture, a scar, but it could simply be a product of the laws of chance, a cosmic coincidence that tells us nothing except that we're still very small and the universe still doesn't owe us answers. In the end, no one can say with certainty what the cold spot is: a supervoid, a collision with another universe, or just an anomaly, a random cold patch in the oldest light we can see. We don't know, and we may never know. But maybe that's the point, because what the cold spot really reveals isn't just about physics or cosmic maps. It's about the limits of our understanding. We often think of science as a process of answers, but more often, it's a process of better questions. The cold spot isn't a discovery. It's a reminder that the universe is vast, strange, and still full of phenomena that don't fit neatly into our models. That somewhere out there, past the galaxies we can see, past the light we can measure, there may be forces at work we haven't even begun to comprehend. Not every mystery ends in revelation. Some are left open. And for now, the cold spot remains exactly that: a silent, frozen blemish on the edge of the sky, and one of the greatest unsolved questions in modern cosmology. In 2015, astronomers were combing through data from the Kepler Space Telescope, a mission designed to find planets by watching stars flicker. The principle was simple: if a planet passes in front of a star, it blocks a tiny bit of light. Kepler was watching for these dips, little blinks that meant something was there. And then, they found something that didn't make sense. A star in the constellation Cygnus, about 1,470 light-years away, was dimming. But not by a few percent. Not in regular intervals. It was dimming wildly. Sometimes by as much as 22%. That's not what a planet does. It wasn't a clean, symmetrical dip like an orbiting object. It was messy, unpredictable, deep fades, long fades, sudden returns. It looked like something enormous, or many things, were passing in front of the star, but with no pattern. And perhaps most strange of all, the star had been gradually dimming over time, not just in bursts, but overall, year after year. It was unlike anything Kepler had seen. The object was labeled KIC 8462852. But soon, it became known by a different name: Tabby's star, named after Dr. Tabitha Boyajian, the astronomer who led its analysis. And from the moment it was discovered, it became one of the most compelling stellar mysteries of the 21st century. After Tabby's star was discovered, astronomers did what scientists always do first. They tried to explain it using known physics. The first theory was comets. Maybe a massive cloud of icy bodies, like those in our own Oort cloud, had been disturbed by a passing star and were now drifting in front of Tabby's star. That could explain the irregular dimming. Comets are messy. Their tails scatter light. And if a large swarm passed in front of the star, it might produce those strange asymmetric dips in brightness. But the problem was scale. The amount of dimming observed, up to 22%, would require hundreds of thousands of comets, all perfectly aligned from our point of view. That's not impossible, but it's incredibly unlikely. The next idea was dust. Maybe there was a disk of debris, a broken-up planet, or fragments from some recent collision. But if it were dust, it should emit heat. Infrared telescopes should have detected warm particles glowing around the star, but they didn't. Tabby's star wasn't giving off any excess infrared radiation. Whatever was blocking the light, it wasn't warm. Other ideas followed: a warped star, an enormous ring system, a cloud of dark matter. All of them had the same problem. They didn't match all of the data. And as the explanations got weirder, the question shifted. What if this wasn't something natural at all? As natural explanations began to fall away, a more radical idea started to emerge. What if the strange dimming of Tabby's star wasn't caused by comets or dust or anything natural at all? What if something artificial was orbiting the star? It was a question few astronomers wanted to ask, but one that couldn't be completely ignored. The idea came from a concept first proposed in the 1960s by physicist Freeman Dyson. He imagined that an advanced civilization, far older and more capable than ours, might eventually try to capture the energy output of an entire star. To do that, they'd build enormous structures, orbiting satellites, panels, or shells, designed to collect starlight. These structures became known as Dyson spheres, not solid balls surrounding a star, but swarms of megastructures, slowly being assembled over centuries or millennia. From a distance, they would block a portion of the star's light, but wouldn't necessarily emit any infrared heat of their own. The behavior of Tabby's star, the deep, irregular dips, the lack of thermal signatures, matched some of what a Dyson swarm could theoretically produce. It wasn't proof, it wasn't even strong evidence, but it couldn't be ruled out. For the first time, a real star had raised a question that science had mostly kept on the edges. What if we just found something built? SETI, the search for extraterrestrial intelligence, quickly turned its radio telescopes toward Tabby's star, scanning for any kind of transmission. The results? Silence. No signals. No beacons. Nothing to suggest intelligence. Still, the star kept dimming. Over the years, Tabby's star has been watched closely. New telescopes tracked its brightness. Spectroscopy was used to analyze the type of light being blocked. And slowly, a new theory emerged. One that could explain most, though not all, of what we see. Interstellar dust. Not the thick, warm kind that glows in infrared, but incredibly fine-grained particles, drifting through space, thin enough to block visible light, while remaining too cold to be detected in other wavelengths. Some studies suggest the dips in brightness are wavelength dependent, meaning different colors of light are being blocked at different levels. That behavior is more consistent with dust than with solid objects. And for many astronomers, that's now the leading theory. It's a simpler explanation. It doesn't require comets, megastructures, or interstellar engineering. Just dust. But not everyone is satisfied. The overall long-term dimming of the star, a steady fade over decades, still isn't fully understood. And some of the deepest dips in brightness are hard to explain with dust alone. So the debate continues, not just about Tabby's star, but about what we consider possible. It's easy to say aliens when we're confused, and just as easy to dismiss every strange observation with, "It's probably dust." But Tabby's star lives in that gray zone, where nothing quite fits, and where even the best models still leave unanswered questions. Tabby's star hasn't given us answers. No breakthrough, no signal, no reveal. Just light that dims when it shouldn't. But maybe that's why it matters. In science, it's easy to chase clean conclusions, data that fits a model, equations that resolve. But real discovery often begins at the edge of confusion. Tabby's star didn't show us aliens. It didn't shatter physics. But it did remind us that the universe is full of systems we still don't understand, and that even ordinary stars can behave in ways we didn't expect. That's the value of mystery. It keeps science honest, curious, humble. Because if a single star in a quiet patch of sky can challenge decades of observation, then what else is out there, still waiting to be seen? What patterns have we missed? What signals have we already ignored? And how many answers will begin, not with certainty, but with a simple flicker of light that shouldn't be there? On the night of August 15th, 1977, something unusual was picked up by a radio telescope in Ohio. The telescope was part of a project known as SETI, the Search for Extraterrestrial Intelligence. It was scanning the skies for radio signals that might hint at life beyond Earth. The system being used was called Big Ear, a giant fixed antenna array that listened to one slice of the sky at a time as the Earth rotated. For most of its life, Big Ear heard nothing but background noise, static, star chatter, interference. But that night, it heard something else. A strong, narrowband radio signal coming from the direction of the constellation Sagittarius. It didn't drift. It didn't spread. It was clean, focused, powerful, and it lasted 72 seconds. The intensity of the signal rose and fell, exactly as it should if it came from a fixed point in space, passing through the telescope's field of view. When the data was printed out, it didn't look like noise. It looked like something real. Astronomer Jerry Eman, reviewing the data later, was so surprised. He circled the signal on the printout and wrote just one word next to it. Wow. That one word would give the signal its name, and in the decades since, no one has ever heard it again. The wow signal wasn't just strong, it was precise. Most natural radio emissions, like those from pulsars or quasars, are broadband. They span a wide range of frequencies. But the wow signal was narrowband, extremely narrow, just a few hertz wide. That's exactly what we'd expect from a deliberate transmission. And the signal's strength followed a very specific pattern. It gradually rose, peaked, and faded, exactly as expected for something fixed in space as the Earth rotated past it. It didn't repeat, it didn't stutter. It behaved like something real, coming from a fixed point in the sky. The frequency was also important. It was centered at 1420 megahertz, the exact frequency emitted by neutral hydrogen, the most common element in the universe. That frequency has long been considered a natural hailing frequency, a universal channel that any intelligent civilization might use to communicate. In other words, if someone were trying to say hello across the stars, this is exactly how they might do it. But despite all of this, scientists were cautious. Could it have been a satellite? A signal reflection from Earth? A classified transmission? Every possibility was considered. But the signal didn't match anything man-made, and no known astronomical object could have produced it. It didn't come from the Earth. It didn't come from the moon. It came from somewhere else. After the WOW signal was discovered, astronomers did the only thing they could. They looked again. The Big Ear telescope was pointed back toward the exact same region of the sky, night after night, month after month, but the signal never returned. Other observatories joined the effort. The Very Large Array in New Mexico, SETI's Allen Telescope Array in California, even powerful instruments in Europe and South America. All of them listened. Nothing. Not even a faint echo. Whatever caused the signal, if it was real, either stopped transmitting or was so precisely timed that we happened to catch just a single, fleeting transmission. Some scientists believe we may have only caught part of the message, that it began before we started recording or continued after we moved on. Others suggest it might have been a kind of cosmic coincidence, a combination of natural sources blending together for just a moment, never to align again. There's even speculation that it may have been intentional, a one-time ping from a distant civilization, a test, a probe, a signal to whoever might be listening. Once. But none of these are more than theories. The truth is simple and frustrating. In more than 4 decades, the WOW signal has never repeated. It came and went, once, and it left behind only a few lines of printout, a single handwritten word, and a silence that still hasn't broken. Over the years, many explanations have been proposed. The most common? That the WOW signal was the result of Earth-based interference, a signal from a satellite, a military transmission, a reflection off space debris. It's possible, but it doesn't fit cleanly. For one thing, the WOW signal was only detected in one of Big Ear's two radio beams. If it had come from a nearby source, like a satellite or aircraft, it should have appeared in both. Then, in 2017, one new theory gained attention. A team suggested that the signal might have been caused by a passing comet, specifically Comet 266P/Christensen, which was in the same region of sky at the time. Comets can emit hydrogen at radio frequencies, and 1420 MHz, the WOW signal's frequency, corresponds to the hydrogen line. But again, there were problems. Comets don't usually produce signals that strong or that clean, and no other comet since has produced anything similar. Even the original authors of the comet paper admitted they couldn't replicate the signal. So where does that leave us? Not with answers, but with possibilities. A one-time transmission, a natural cosmic fluke, or the briefest, faintest handshake across unimaginable distance. In the end, the WOW signal may never be explained, but it forced us to ask, if a signal came from the stars and no one heard it again, would we even know it was real? In 2007, an astronomer was going through archived telescope data, not live feeds, just old files, forgotten logs. And in one of them, he found something that should not have been there. A sudden, high-energy pulse, lasting just a few milliseconds. The signal came from deep space. It was brief, powerful, and it showed no signs of being man-made. The astronomer's name was Duncan Lorimer, and the burst he discovered would become the first of what we now call FRBs, fast radio bursts. Since then, dozens, now hundreds of FRBs have been detected, each lasting just a fraction of a second and coming from billions of light years away. They're some of the most energetic radio events in the universe. In the time it takes to blink, an FRB can release more energy than our sun does in days. And for a long time, every single one was a one-off. It was as if the universe was whispering strange, brief messages, never repeating, never clarifying, and no one could figure out what they meant. After the first FRB was found in 2007, astronomers didn't know what to make of it. Was it a glitch, a fluke? It wasn't until 2013, 6 years later, that more bursts started to show up, each one with the same basic signature: short, sharp, incredibly powerful. They were all over the sky, no pattern, no origin point. And for years, every fast radio burst was a one-time event. That made them hard to study. Telescopes had to be in the right place at the right moment, listening to the right patch of sky, all for a signal that would vanish in milliseconds. But then something changed. In 2016, astronomers detected the first repeating FRB. It came from the same spot in the sky, again and again, irregularly but undeniably. The signal was named FRB 121102, and it was the first clue that some of these bursts might not be random. They were coming from galaxies billions of light years away, yet they were repeating, as if something out there was generating them, on purpose. Then came the second repeater, and the third. Some began repeating every few days. One even repeated on a strict 16-day cycle, silent for 12 days, then bursts for 4. These weren't flukes. Something, somewhere was doing this, and doing it over and over again. As more fast radio bursts were discovered, the race to explain them intensified. The first major theory pointed to neutron stars, the incredibly dense remnants of collapsed supernovae. Some neutron stars, called magnetars, have unimaginably strong magnetic fields, trillions of times stronger than Earth's. These magnetic monsters can snap and shift like earthquakes, releasing bursts of radiation. It's possible that FRBs are caused by these magnetic quakes, brief flashes of energy beamed across the cosmos. And in 2020, that theory gained support when a nearby magnetar in our own galaxy emitted a radio burst very similar to an FRB. But it was much weaker. To match the energy of distant FRBs, magnetars would need to be doing something more, or something else entirely. Other theories suggest collisions, two neutron stars merging, or a black hole consuming a stellar remnant. These events could produce bursts of energy strong enough to mimic what we see. But they're catastrophic, one-time events, and they don't explain the repeaters. So the mystery remains, and with it, a quieter, more speculative idea that these signals might be artificial. The power levels, the narrow frequency bands, the repeating cycles, all of them fall within the range of something that could be designed. Not proof, not evidence, just possibility. The kind that's hard to ignore when the data doesn't quite line up. As instruments became more sensitive, the bursts became stranger. Some fast radio bursts weren't just repeating, they were sending out signals with structure. Bursts broken into subbursts, frequency sweeps that looked almost coded. Others showed polarization, meaning the waves were spinning, twisted by powerful magnetic fields. That suggests these signals are coming from extreme environments, places near black holes, neutron stars, or other dense cosmic objects. But even then, some things don't add up. A handful of fast radio bursts have been detected with nearly identical profiles, despite coming from opposite sides of the sky. Some appear to drift in frequency, not randomly, but in a way that almost suggests design. There's even speculation that some of these bursts might contain information, though no data has ever been extracted. And then there's the silence. Some fast radio bursts repeat dozens of times, then stop completely. Others appear once, then never again, like the wow signal, but louder. No single model explains all of them. Each new discovery seems to raise more questions. Are we seeing the same phenomenon in different forms? Or are FRBs not one thing but many, each with its own strange cause? We still don't know what causes fast radio bursts. We don't know why some repeat and others don't. We don't know if they're the result of collisions, magnetars, or something we haven't even imagined yet. But we do know this. The universe is talking. Not in words, not in language, but in pulses, in patterns, in bursts of energy that race across billions of light years, only to vanish in the blink of an eye. Science has always been about finding signal in the noise, but FRBs blur that line. Some of them seem natural, others don't. Some feel like echoes of violent events, others feel like something more. We don't know which ones are which, and maybe we're not supposed to, not yet. But the search continues. The sky is full of static, and somewhere in that static, something is speaking. Whether it's a dying star or something else entirely, we're listening. Galaxies don't just sit still. They move, they spin, they orbit, they drift through the cosmos. And for the most part, we understand those motions. Galaxies are pulled toward each other by gravity. They move in clusters, drawn toward dense regions of mass. But in the 1970s and 80s, something unusual was noticed. A vast region of the universe, including our own Milky Way, seemed to be drifting in one particular direction. Not because of nearby galaxies, not because of expansion, but because of something else, something big. The motion was subtle, about 600 kilometers per second, but it affected thousands of galaxies across hundreds of millions of light years. All of them, moving toward a single point. The region was nicknamed the Great Attractor, And for decades, we didn't know what it was, only that something, somewhere, seemed to be pulling everything in its direction, including us. For decades, astronomers tried to find out what was pulling everything in. They pointed telescopes toward the source of the motion, a patch of sky in the direction of the constellations Centaurus and Norma. But they ran into a problem. That region of space sits behind something we can't look through, the zone of avoidance. It's the part of the sky blocked by our own Milky Way, filled with stars, dust, and gas so thick that even our best instruments struggle to see past it. It's like trying to observe a galaxy through the center of a bonfire. What we can detect are subtle clues: infrared heat, radio waves, and gravitational effects on nearby galaxies. And from those clues, a blurry picture starts to form. In that direction, hidden behind the dust, lies an enormous structure, a dense concentration of galaxies and dark matter, a supercluster known as the Norma cluster. It's hundreds of millions of light years away, and massive enough to distort the motion of everything around it, including us. But even this doesn't fully explain the motion we're seeing, because what lies beyond the Norma cluster is even stranger. In 2008, a team of scientists led by Alexander Kashlinsky noticed something strange. Galaxy clusters, enormous structures made up of hundreds or thousands of galaxies, were all moving in the same direction, not just within our local region, but across billions of light years. Their motion couldn't be explained by gravity from the Norma cluster, or any known structure. This wasn't a local drift, this was a cosmic flow. The team called it dark flow, a steady motion of galaxy clusters all heading in the same direction, as if something enormous was pulling on the fabric of space itself. But here's the problem. That direction leads beyond the observable universe, beyond what we can see, beyond what we can measure, and beyond what current physics can fully explain. Some theories suggest there may be large-scale structures outside our cosmic horizon, clusters of matter we'll never observe, but which still exert gravitational influence. Others go further, proposing bubble universes or higher dimensions, or that our visible universe is just one piece of a much larger structure we can't yet perceive. There's no consensus, but the data remains. Hundreds of galaxy clusters, spread across billions of light years, are all drifting in the same direction, and we still don't know why. We like to think we understand the universe. We've measured its age, we've mapped its background radiation, we've watched galaxies form, merge, and drift apart. But dark flow challenges all of that, because if something outside the observable universe is influencing the motion of everything inside it, then what we see, everything we've ever observed, might be only a small part of a much larger, hidden reality. A universe not bounded by what light can reach, but by what we're able to perceive. Something beyond the cosmic horizon, unseen, unmeasured, and possibly unknowable. And yet, it pulls on us, quietly, relentlessly, like the tide. We don't know what the great attractor truly is. We don't know what causes dark flow. But we do know this. Something is out there. Not a theory, not a prediction. A motion, a drift. A gentle cosmic pull that even our galaxy seems unable to resist. And we may never know what lies at the other end. A black hole is not a thing, it's a boundary. A place where space collapses in on itself, where gravity is so strong that nothing, not even light, can escape. At the edge of a black hole lies the event horizon, a line you can cross but never return from. Anything that falls past that line is gone, forever. For centuries, black holes were just theoretical, the solutions to equations that described things too dense to exist. Then we started finding them, at the center of galaxies, in the remnants of collapsed stars. We watched them bend light. We watched them devour matter. And in 2019, we even saw one, the now famous image of a black hole in the galaxy M87. But for all we've learned, black holes still don't make sense, because there's a fundamental contradiction at the heart of how they work. A paradox, one that pits two of the most successful theories in science directly against each other. According to Einstein's general relativity, when something falls into a black hole, it's gone, crushed into a singularity, a point of infinite density where space and time collapse. And whatever information it carried, whether it was a planet, a photon, or a particle, is lost forever. But that's a problem, because according to quantum mechanics, information can't be destroyed. That's not a suggestion. It's one of the most deeply held laws in physics. Even when particles interact, split, or disappear, their information must be preserved. So what happens when those particles fall into a black hole? If relativity is right, the information vanishes. If quantum theory is right, it doesn't. Both theories have been tested to extreme precision. Both work. But they can't both be true. Not here. This is the heart of the black hole information paradox. And it's not just a niche physics problem. It's a crack in the foundations of science. A sign that our best theories may be incomplete. Somewhere, something is missing. And for decades, no one knew how to fix it. In 1974, Stephen Hawking made a shocking prediction. Black holes aren't completely black. Using quantum mechanics, he showed that black holes should emit a faint stream of particles, something now called Hawking radiation. It doesn't come from inside the black hole. It forms just outside the event horizon, where empty space isn't truly empty. According to quantum theory, the vacuum of space is filled with virtual particles, pairs that constantly appear and annihilate one another. But near the edge of a black hole, that process can be interrupted. One particle falls in, the other escapes. To an outside observer, it looks like the black hole is slowly losing mass, bleeding energy into space. Over time, it shrinks, and eventually, it disappears. A black hole can evaporate. But here's the catch. Hawking radiation is thermal. It's random. It doesn't seem to carry any information about what fell into the black hole. So if a black hole eventually vanishes, and the only thing left behind is random heat, then where did the information go? According to Hawking's own calculations, it's gone forever, which violates quantum theory. Hawking had taken a step forward and made the paradox worse. In the years since Hawking's prediction, physicists have proposed bold, sometimes radical, ideas to resolve the paradox. One of them is called the firewall hypothesis. It suggests that the event horizon isn't a smooth boundary, but a wall of energy, one that burns anything that tries to pass through. That would destroy information in a new way, and violate Einstein's predictions instead of quantum mechanics. Another idea is the holographic principle. Proposed by Gerard 't Hooft and refined by Leonard Susskind, it suggests that everything inside a black hole, the mass, the matter, even the information, is somehow encoded on its surface. Like a hologram. This theory implies that reality, even outside of black holes, might work the same way. That the universe we live in is a projection from a lower dimensional boundary. It's not science fiction. It's serious physics. And it's gaining traction. There are other theories too. Quantum gravity, entanglement bridges, even the idea that black holes might preserve information in subtle patterns within the Hawking radiation itself. None of them are proven. All of them are controversial. But they share one thing in common. They suggest that our understanding of space, time, and information is incomplete. That at the edge of a black hole, where physics begins to break, We might be staring into something deeper, a hidden structure beneath reality, waiting to be understood. We live in a universe that's 13.8 billion years old. We've sent probes beyond our solar system. We've mapped the cosmic microwave background. We've built models, equations, and machines that can look into the past and predict the future. But even now, we are surrounded by questions we can't answer. A cold spot in the sky that may be the scar of another universe. A star that dims for no known reason. A radio signal, heard once, never again. Repeating bursts of energy from deep space. Galaxies drifting towards something we can't see. And black holes, where the laws of physics begin to unravel. We like to believe that science is about certainty, but in truth, science begins where certainty ends. The mysteries we've explored aren't proof of aliens, or other universes, or cosmic structures beyond comprehension. They're something more powerful than that. They're reminders that we are still early in the story, that the cosmos is not obligated to make sense to us, and that mystery is not a weakness of science. It's the fuel that keeps it moving forward. Every now and then, we catch a glimpse of something strange, a flicker, a signal, a silence that doesn't sit right. We don't always understand what we're looking at, but we look anyway, because that's what it means to explore the unknown, to live at the edge of what's known, and keep asking questions.